Maybe from other talks, he's been doing hardware hacking and testing. He does training in the area and has been doing this hardware taking things apart for UK. And we're looking forward to hearing the chilling tales.
Hello. This is the dirty secrets your hardware keeps and how we can clean up its act. So that's me. My name is Joe FitzPatrick. My background is electrical engineering. I did a degree in electrical engineering, a master's degree with a lot of focus on computer science as well, computer engineering aspects of it, as well as information security. But what I ended up getting into was silicon debug, fault failure analysis of silicon systems for several years, which got me very deeply intertwined with the inner workings of some CPUs, which led very easily into some hardware pen testing of desktop and server parts. So after doing a few years of hardware pen testing, which not many people really get the opportunity to do because there's a pretty small crossover of hardware and security, I decided my time would be better spent kind of doing training. So I was doing training internally where I used to work, and then for the past 3 years I've started my own company focused on doing some hardware security training. So who recognizes this? This is the standard HP financial calculator. This is, if you ever go and try and get a financial advisor or someone money related, if they know how to use this calculator, they probably know what they're talking about. If they don't know how to use this calculator, go find someone else, right? But this is a calculator, it comes in, uses batteries, you can use it, you can rely on what it does. How many of you would trust your life savings to this thing? In the hands of a skilled operator? Okay. Now, if we take a step further, let's say we got this HP 12C emulator for the iPhone, and your financial advisor goes and uses that, pulls out his iPhone 6 Plus, and he starts, doing, all the annuity calculation stuff. I don't know any of that stuff. I just know that they use this calculator. Would you trust that calculator any more or less than you would the standalone calculator? So if we take it a step further, here we have a JavaScript implementation of the same calculator running on someone else's, well, technically the JavaScript is running on your computer, but you're going and fetching someone else's code and running it on your computer, in your web browser, to go and decide how much you need to save before you can retire. So which one would be the easiest to tamper with? Which one would you trust your retirement to? And why? Right? I would propose that we trust hardware implicitly. In all reality, this hardware calculator is kind of the most difficult to access, the most difficult to get to, right? If you have a phone that has other malware on it, you've got a phone with malware on it. What do you do? If you have a web page that is from some strange epxx.co URL, who knows how many things are in the middle. It is actually an SSL website, so you have a slight bit of confidence because it has the little lock icon. But really, hardware is not all that different from software when we get down to tampering with it, manipulating the things that it can do. So we trust this hardware implicitly. We ought to stop doing that. Software people, even professional software security people, think once it's on the hardware, oh, well, it's hardware. We can't change the hardware, but we'll just trust it. So I'll go through a couple different points. We'll start out with what does hardware security actually mean to me? Because I use the term a lot, and I find that a lot of people use it differently than I do. So physical security is not hardware security, right? Just because we can lock something up and prevent someone from physically touching it does not mean we have secure hardware. An example are these Netgear routers. As of 2 weeks ago, there was yet another remote vulnerability on a Netgear router. When we talk about hardware hacking, hardware reverse engineering, I teach classes based around these routers because they're inexpensive, they are easy to open up, they're easy to find, debug connections to reverse engineer, attack, and interface with the system. So it's a hardware device, but even if you had hardware security in mind, even if you disabled all these debug features, we're dealing with a remote attacker on our hardware device. supply chain security is not hardware security. There's a lot of people who will say if you want, a really secure network adapter, you need to get a bunch of citizens from your country to have clearance and design the silicon chip and manufacture the silicon chip and assemble the board and package the board and ship the board directly to the recipient of the board. And once we've done that, once we've established this secure supply chain, we can finally trust this network adapter. Except that in 2010, when researcher Rigo, he kind of showed that basically you could take a network adapter and give it a remote over-the-wire firmware update. So send a magic packet, your firmware is updated, this is no longer a secure network card, right? Even though everyone who built it had security clearance and was trusted and was a good person, we still will deliver insecure hardware even with a secure supply chain. And finally, secure firmware is not hardware security, right? Just because we can go and we can write firmware and maybe we can use provable logic and math and formal verification to prove that our code is just right. But when we get down to it, this is the main board from inside of one of the monitors I use. Okay, not a TV, it doesn't have like web apps, it doesn't play Netflix, it's a monitor. I hook up an HDMI port or a display port to it, and it puts pictures that I look at, and all of my emails that I send, and everything that I type, and then PGP encrypt. This board is running a MIPS CPU and running an installation of Linux, and it has drivers for network adapters, and it has a serial console that's unlocked. So this is the world we're in. This is my monitor, okay? Anyway, the point is hardware security depends on all these things. So we need to have physical security, we need to have supply chain security, we need to have software security, we need to have firmware security, all working in order for us to think about hardware security. So my background, what are some different ways to tamper with hardware? My background, I've been tinkering with hardware my entire life. Professionally, I've been tinkering with hardware for a decade. Most of my experience is consumer electronics type stuff. So computers, phones, all that stuff, game systems. Very new to the whole industrial control type stuff. But I figured I'd take a look and see what I could apply that I've done on other systems here. So this is a project I worked on a little while ago, and this is called Alloy Viper. So the NSA Playset is a group of us who've gone and re-implemented a whole bunch of the items that we found in a leaked catalog of NSA toys. NSA spy devices, hardware implants that could go and surveil people and stuff. It was leaked about 1.5 years ago, and the media thought it was pretty crazy, all these magic things that the NSA could do, and those of us who tinker with hardware were like, oh wow, I could do that for $20 in parts. So this one was Alloy Viper, and inside of this black box that you see is a PCI Express device that I designed that does memory dumps. So you hook this up to your computer, and I'll read the entire contents of your memory, and I can do offline analysis. I can extract your keys, I can do whatever I want, or I can use it to write memory while I'm connected and bypass your login password, stuff like that. But people are wise to this, so people generally don't plug things into their computer they don't trust. So how can I fool someone to plug this in? What I did is I took a Thunderbolt cable. Thunderbolt is the port that Apple uses for their high-speed data transfer. I disguised it to make it look like a really junky old VGA cable with an adapter already attached. So you show up with your MacBook to give your presentation, you put your MacBook down, and you're like, oh wow, they already have the adapter for me. You plug it right in. What you don't realize is you're not plugging in DisplayPort to VGA adapter that's showing up on the screen. You're plugging a Thunderbolt cable that looks like that goes into this little box that passes through your display to the actual VGA cable. This box could be hiding underneath the stage over here, right? So we're using kind of just basic physical deception to convince someone to expose themselves to a hardware vulnerability. Another project I worked on was SolderKey. So this was based off of a project the NSA had, which would basically be a JTAG implant for certain models of Dell servers. They would receive a server before it was shipped to a customer of interest. They would solder a header onto the board, they would plug a board into it, and would connect to JTAG pins. JTAG is a debug port that lots of CPUs have. And And the purpose of this implant would be to reinstall some malware in case the end user wiped the BIOS, wiped the hard drive, replaced everything else. So this is pretty cool, but again, the NSA plays that is trying to make it accessible and easy. So we threw together this little PCB, which had about $6 worth of parts on it that we could connect to a JTAG adapter, and we could load it up with a payload of JTAG commands that would play back. And the one it is set to do right now is basically it would escalate a user shell. So you're sitting on a console with just user Joe, and every time this thing triggers, it would go and modify that so you're suddenly root. So it turns magic spell that turns user shells into root shells. This other project, this one was done by Mike Osman and a few other people. It looks like a USB cable, right? You see the little plastic shroud and the little metal thing. It looks a little sketchy, and you see there's a mold next to it, which should make you suspicious. Inside of that little rubber connector housing is a wireless radio and a USB hub. So you plug this in, you're not using a USB cable, you're using a USB cable. You can also have malware that goes and sends wirelessly exfiltrated data off of your system. So all of these things, we're taking hardware that we see, we know, we trust, we expect to do a certain deed because it looks like it does, and does something different. Another neat example of hardware modifications that I've been taking a lot of interest in is mod chips for game consoles. I'm not much of a gamer, but I own lots of video game consoles. I get the console, I modify it, and then it sits in a box. So what we see here is a drive chip for a GameCube. It sits on the board. It's a tiny little chip, about an inch square, and it's so easily designed that there are little cutouts right where you need to solder, lined up right where you should solder it. So you buy this chip for a couple bucks, you place it at the right spot in your GameCube, and you get a soldering iron and some solder, and touch, 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 and you've modified your GameCube to play backup copies of games, because everybody backs up all their games in case you have a fire, right? The point, it's easy, right? Someone has, maybe not for to attack something else, but to attack their own system. They want it easy, quick, and possible to just plug this in and go. The mod chips that everybody wants are the ones that you don't have to solder, because soldering is so hard, but you just find a friend who can solder, and you're set. And finally, the other thing we need to consider when we talk about hardware is firmware, because you ask a software person and they'll tell you firmware is hardware, and you ask a hardware person and they'll tell you firmware is software. So it gets lost in between. This is a screenshot of some code grabbed. Kaspersky Labs did a whole bit of analysis of some malware they found that was actually going and infecting hard drive firmware. Since they released this, several other people have gone and published some of their own work on reverse engineering hard drives. And you have a hard drive that sits in your system and serves data, but that hard drive has a CPU on it, sometimes a dual or triple core CPU that's processing all the stuff it's doing. It's pretty feasible to go in there and put a backdoor in your hard drive that waits for you to write certain values to your hard drive and saves them off. So you can, if you write a key file to your hard drive, you can save it. So even after you've deleted the contents of the hard drive, it's still storing a copy. It's a computer, it's programmable, you can get it to do whatever you want. So the point is, there's a whole bunch of ways we can tamper with devices, there's a whole bunch of ways we can make hardware that does things we don't expect hardware to do, but we just kind of trust our hardware, which we shouldn't do. So I talked to some friends, found some people who had some PLC systems I could take a look at. I've never used a PLC system before, I just got my hands on these and said, let's see what I can find. So this is I guess a pretty old system, an S7200 by Siemens. And I look at it, and you've got basically outputs on the top, inputs on the bottom, and you give it power and it does stuff. You have software, you can program it, but I don't care about the software. A lot of people have looked at the security of how these things interconnect and talk, but I'm interested in what's inside the box, so I open it up. First thing that stands out to me is we've got a CPU, it's got a part number, it's made by Texas Instruments. Keep that in mind, I'll keep looking. I also noticed this chip, I can tell just by the shape of the chip that it's RAM. This is memory that the CPU is probably using, and right next to it is a flash chip. So whatever code is executing is probably on that flash chip. Today you have a couple options where you can actually get these CPUs that will encrypt everything that goes off off-chip. They'll use encrypted memory, they'll use encrypted flash storage. I highly doubt that's the case in here. There are a few ways that I could actually go and get the contents of those chips off without removing them from the system, but the easiest thing to do is just get a hot air gun and pull the chip out, put it in a universal reader, and I have a copy of the firmware. I know exactly what this thing is doing. I can always modify it and put it back in. But still, let's keep looking. I take that board off. It's pretty easy for me to conclude this is the logic board. This is the one that does stuff that's interesting, and figures out what to do. The board underneath it is actually connected to all those screw terminals. So this is the board that actually connects the relays, makes stuff go on and off. In my mind, if I'm designing an electrical system, I kind of isolate the different logical blocks. So my guess at this point is those two header connectors that connect to the other board, those are just carrying like the digital logic signals that say this should be on, this should be off, and all of the regulation is happening on this board. I pull that off. Oh, yeah, so we've got some output buffers. These chips have model numbers on them. I can look them up pretty easily. I didn't even need to look up the chips to figure out that's probably what they're doing now. And at the bottom, you have input buffers. Looking right underneath that, there's yet another board. This is a pretty simple one. This is just the power supply, and it breaks down into a couple of different voltage transformer into the right voltages for this system. So we'll ignore this one for now. Pop back up to this layer. I get a multimeter, measures voltages and resistances and everything, and mine has a little beep mode. You put it in beep mode, and when the two wires touch, it beeps. So then I go through and I look at all these chips, and I touch the little legs, and I figure something's got to connect to these header. Sure enough, these 4 chips, which are your input buffers, all connect to this header. These 7 chips up here all have pins that connect over to this header on the side. Okay, so let's look at that header. What I see is a 0.1 inch, how many pins is that? 14 pin header. So if I wanted to modify something in this system, this is the easiest spot to do it. So from an electrical perspective, one second before I get there, I might look at the system and see if it's possible for me to just directly set those pins if the inputs and outputs are well protected. I can probably just do that and it wouldn't matter. But it's always good to be careful and cautious, especially if you're tampering with someone's system that does something important. Critical system, whatever, you got words for these, right? Critical system. So I threw together this thing. On the left side is a Nordic Semiconductor NRF 24LO1 Plus radio and a little chip antenna, PCB antenna. That board runs less than $1. On the right side is an Arduino Pro Mini. It's got an ATmega 328P processor. That board might run almost $2 if you buy them individually. So all told, there's $3 right there. What this is a programmable chip. It has input and output and a radio. 2.4 gigahertz radio. So I get that thing, I solder some wires on the end which are going to connect power and ground and put in an output signal, slip it in a plastic bag so I don't short anything out. When I go ahead and put the top back on, it completely conceals my addition, my Easter egg that I added to this board. Pop the top back on, and who can see the modification that I made? Another thing I didn't mention, I've got these plastic clips on the side, right? It was pretty easy for me to just stick a fingernail in and pop the whole top off. There's no scratches, no marks, no bends, no breaks. It was really easy for me to get this thing open, put something in, and take it out. So full disclosure, I did not actually make these modifications to the system to actually test it working. I do have some firmware I put on there, so theoretically it should work, but this is someone else's equipment. I didn't want to go and start soldering things to it. So I will continue to badger and perhaps go and just buy my own and actually modify it. But essentially what I would do is I would connect these 2 pins to a couple of these pins. And what would happen is as in normal mode, the device would be powered, it would just pass through all the data. This microprocessor runs at about 16 megahertz. There'd be a slight latency for passing on that signal, but that latency would actually be on the order of like 120 microseconds, which is a fraction of a millionth of a second, less than a millionth of a second. So perhaps that's a difference that will be registered, but I highly doubt it. When I want to, I get another radio at the same frequency, and I just tell it to set the pin. And instead of outputting the value it receives from here, it'll output a different signal. It'll turn motor on to off to on. I have full remote control. And then, when I'm done, I clear it, and it goes and it just passes through the signal that received. I don't know how deep into microcontroller programming you guys are interested. Basically, I set up an interrupt on one of the pins. So every time that the pin toggles, it runs a tiny snippet of code, and that tiny snippet of code changes the output, unless I have wirelessly told it to do something else. So $5, 5 minutes of popping things off and popping them back on, and we have put a wireless backdoor into this cool little cheap system. So what? There's no software changes needed. The device is still intact. It's still the original hardware. No modification is apparent from the outside of the device, and one single signal can wirelessly set or unset a pin that I've chosen. If I wanted to, I could manipulate it and make it a little more advanced and have it do all 8 signals, but I figured one was good enough for a proof of the idea. What's also interesting is that same header that we were looking at over here connects to this programming port right here through this chip right here. This chip is a buffer chip. But basically what that means, if I wanted to, I could see any traffic that comes in or out. I could have a more complicated microcontroller there that would modify anything in flight, that would spoof anything I wanted to. But again, that's another layer of detail that you could always push at if you wanted to. So onward, that's not, that wasn't the only device that I got my hands on. I got my hands on this Phoenix contact system. I didn't take it apart because it was a little more difficult to take apart, and we'll see what I did take apart in a minute. But I went to the website, this is the web interface on the device. So you have it configured, installed, and powered up. You hook your cable up to it, and you navigate to this web page, and you can see the status of your system. That's pretty cool. How does it do that? Well, I went to their website and found a firmware update. Okay, so what can I do with this firmware update? I didn't have to go and open the device to grab this firmware out of it. I just downloaded it from the manufacturer. I unzip the file, and it has a how-to.txt file, which probably tells me how to flash it, and a webserver.img. That sounds good. I used a tool called binwalk. It's a firmware analysis tool that goes looking through binary images for files that it recognizes, and it tells me it's finding all these zip compressed files. They're in a strange format, they're all crammed together, so if I wanted to, I could extract a whole bunch of JavaScript files, a whole bunch of CSS files, but I still don't know the format of this file. So you probably can't see any of the details in the slide, but the patterns are what are important. This is looking at the file in raw format. At the side here, this is the ASCII format that shows a whole bunch of file names. Looking at this, I see a lot of patterns in the file, and I also see some numbers that increase as I go down. If I look at more detail, beginning of the file, I have a pattern 1FF1. My guess is that's like a magic number. The file starts with 1FF1 so that we know it's valid. I look over, I see a number that corresponds to the address where this header table ends. A number that equals the number of entries in this table. And then a whole bunch of entries. And each entry has an address in the file, an offset in the file, and length of that offset. So we see this 144, I think this is offset by 1. This 144 plus 4 gives us 148, plus 40 gives us 188, right? So we can walk through the file and know what we're going to find in this file. Point is, this is 5 minutes of work for me. Like, I went through, I grabbed a firmware image. I didn't have to physically retrieve it from the device, but I was able to grab a firmware image, look at their file. There's no apparent signature in the file. Could be the case. There could be something in there that I'm not catching. Again, I didn't go and flash these modified firmware images because this is someone else's equipment. It's pretty simple. It's a non-standard way of bundling the files together. But what this contains is a bunch of code, right? It is just a web page, but it's code, some of which runs on web server. More importantly, some of it runs on the administrator's computer. Okay, so what fun things can you put in JavaScript that you know an administrator is going to go and use. It doesn't appear, again, to have any sort of signature, cryptographic signature or CRC. It just grabs all those files together, appends them one at a time. This is standard for embedded systems. This is the kind of effort that goes into stuff like this. On the bright side, the vendor's website did actually force me to use SSL to download this. I've dealt with a couple microcontroller manufacturers where I want to write some code for a microcontroller, and I can't actually get the SDK from an SSL, SSL web server. Right? I can only download it in plain text. It only runs on Windows, so it's like, oh, I'll go on the internet and download the exe files and run them. So I use Tor for that, just for safety. Because no one adds stuff to stuff you download on Tor. So, still playing around, found another device. This is another Phoenix contact system. Once again, it's a couple plastic clips that you pop off, and you open the thing right up. There's no indication that I opened it. I don't have to break anything. I don't have to scratch anything. And as soon as I look inside this, I get excited, right? Does anybody see it? Anything? No? Well, so first thing I see over in this corner right here are these 10 pins, 0.05 inches apart. I can tell you right now, just by seeing that pin, that there's an ARM microprocessor here. That's a JTAG port, and it's probably enabled. So sure enough, I look, and it's an LPC 1765, which I actually have people dev kits lying around for. That is a JTAG, 10-pin JTAG connector. I can confirm that because I go and grab the data sheet for this chip, and I put my multimeter in beep mode, and I touch, I think it was these pins over here. These pins right here, and these pins right here, and they beeps. Okay, they're connected. That's pretty cool. Now, the other thing I noticed on there is a little flash chip, which I'm not sure what it's used for because this microcontroller has some flash embedded in it that's probably used, but I'm sure there's something good on that chip as well. There is a caveat, right? This chip supports code protection. Code protection is in there to prevent end users from, copying the code and, maybe counterfeiting devices. Again, this code protection is generally like a best effort kind of thing. When you physically own the device, the semiconductor manufacturer pretty much knows that if you have it in your hands, you can probably get that code out. There are 3 levels of settings that you can put this code protection on. And if you wanted to, you could disable this JTAG port so it wouldn't work. I did not solder anything to this board, so I don't know what level code protection is set, but as soon as I get permission from the owner of this piece of hardware, I will. My best guess is it's probably not set. In consumer devices, it's almost never set. One of the reasons it's very rarely set is because if the manufacturer gets a return, they need to figure out why they got a return, and they might use this port. If they've spent the time to put these pins on the board, they want to use them, right? They want to get a return back, they want to use this port to get some information about the chip and see why it's failing. But, let's see. What is also really interesting about this system is when you plop it all back together, snap the top back on, you have all these little modules. You can put a screen down here, you can put a USB port or something in one of these. You have this little plastic thing you pop out, and there's a black header. You can't really make it out underneath there. But these pins are right next to that. So if I really wanted to, I could really just get the plastic blank and glue some pogo pins, little bouncy, like a pogo stick, a little electrical pin that you pop it into place in it. It'll touch these contacts, and so I could just walk by, pop this out, put my JTAG implant in, snap it in place, and who would even know, right? So just fun things like that I like to do with hardware when I see it. So what? JTAG could be disabled. I don't know for sure. It's probably not. Test headers are easy to access on the unit when it's in operation. Really, I just walk up and pop something in. So I could make that pluggable extension module. And in my world, in the hardware world, when you get JTAG, you win. Software people, they can talk about root shells, and those are great. And there are a number of ways you can go from JTAG to root shells, but from a hardware perspective, when you get JTAG working, you win. So onward. What can we do about this? Visually inspecting devices, you can't see firmware, right? You can look up the system, you can examine it, you don't know whether it's been modified or Anything that's human read output, any display that shows up on a screen anyway, it reacts when you push a button. There's no way to truly verify something. Even if you did go so far as have some cryptographic authentication mechanism, when you're talking about hardware, if you're talking about being concerned about counterfeit devices, you can always copy everything that was used to create that cryptographic response to a device, unless you're using a silicon hardware security type module, which most things again don't use. And even then, it doesn't solve the problem; it just makes it a more expensive problem. And finally, one physical modification wasn't apparent even with the case open. All three devices, they pop open, they pop back together over and over again. There's no scratches, no dents, no warranty void if seal broken stickers, anything like that. There are ways around those, but there's just nothing. How about electronic inspection? The very first one, the device pretty much behaved exactly the same because we didn't tamper with any of the electronics. Can we read and confirm the firmware? Yeah, unless we take over the interface that lets us read and write firmware as well. Can we trust, if we have a device that cryptographically authenticates it, can we trust the authenticated device, right? We're not actually solving the problem, we're just passing it off to something else. And finally, what can we do about it? So as users, this may sound like a sales pitch to buy through authorized channels, and it probably should be, but understanding the physical security requirements of the device that you buy is important. The manufacturer should tell you whether you should have this thing under lock and key 24 hours a day, or if it's something they feel it's safe to actually have exposed like an outside environment where someone could potentially walk up to it, touch it, or do something. Having a means of visually and electronically identifying your devices is pretty important. If you have like a serial number etched into it, that can help. It can be duplicated, but there are ways to try and make it less duplicatable. Inspecting your devices regularly, just to keep an eye on them, make sure they aren't changing. These aren't the kind of things that you're gonna go out and check, and if it's there, you see it, it's a piece of hardware, it hasn't moved, it's probably fine. Is our gut reaction, our impulse. How about hardware suppliers? They can do internal and external security reviews. They can authorize and audit supply chains. Just because you have a secure supply chain doesn't mean it's actually the way anything works. So you have to actually go and walk into a supplier and say, I want to buy this device, and actually test to make sure it came through the proper channels. Give users guidance on how to install the devices securely. Give them an idea of what they should expect and how long it might take someone to tamper or modify something. Use a tamper-evident enclosure or enclosures that just can't be opened once the device is installed. By shaping the plastic properly, once the device is latched into the rail and screwed in, right? If it's impossible to get that plastic case off, that's a layer of security. Someone's going to have to use a hammer or a screwdriver or whatever, a saw to get in there, and you'll notice that. Finally, be sure you're disabling debug functionality on production devices, because why does anybody do it? No one disables it. It's just universal. Very few cases do you actually encounter people actually disabling this debug functionality. And finally, with firmware suppliers, same thing. Conduct internal and external security reviews. Figure out a way to securely deliver your firmware files. That means having them signed and not flashing them unless they're signed. That also might mean encrypting them so that people can't even see what's in them. Again, disabling debug functionality, it might make it more difficult for you to figure out what's broken if something's broken, but it makes that device that much safer. And finally, does the vendor actually list who their authorized distributors are, right? I can go to someone to buy a device and they'll say, yes, I'm an authorized distributor. And do I trust them? Oh, they have the logo on their website, they must be an authorized distributor. But manufacturers, they don't want to promote any one vendor over another, so oftentimes they don't put vendor names on their website. But how can you tell if someone's an authorized distributor unless the manufacturer's going to tell you? Do they give end user security recommendations? If their security recommendations sound like a lot of smoke and hand waving and smoke and mirrors, then they probably are. And then just take a look yourself at how easy it is to take apart the device. How long is it going to take you to get your hands on the firmware? If you can get your hands on the firmware within 5 minutes, having no relationship with the company and never heard of the device before, you're probably not in a good situation. So, that is what I have to say about the dirty secrets your hardware can keep. If you guys have questions.
Do you have time for questions? So I hear what you're saying about looking at vendors and especially the resale part of it. And I can't. It seems kind of hopeless because the people reselling changes, and even though they're authorized, they only see a small picture of it, and I'm not sure how to. Should we look into standardization of? I don't know. Some security assessments.
Well, I mean, from a business perspective, the vendor is well suited to know where the devices are going and who's buying them and what they're buying them for, right? I'm not saying you should limit who buys your devices, but if you're selling devices, you want to know who's buying them so you cater to the needs of your customers. So there's some business motivation to have that, from a security perspective, we can add to that and perhaps use that to convince people to keep track of where devices come from and where they go and who they're sold through. Again, my experience is a lot more on the computer side of things, and we look at secure updates for operating systems, right? It's taken us decades to get to the point where we can securely deliver software updates, right? So we finally have this secure channel for delivering software updates, which software is easy because you don't actually have to move anything, you just have to move bits. Hardware gets more difficult. And there have been lots of cases in the past where companies that even have secure supply chains who have authorized vendors that they list, have still managed to get gray market material in that supply chain. Yeah. I was actually thinking of Cisco routers that we found that have some kind of cards in them, but yeah, that was a good one to pick on these days.
Yeah, which takes us right into the next topic. Thank you very much.
Thank you.